think that's okay? Okay? Yeah, alright, sorry. Okay, so my name's Elaine Toogood. I'm an architect and I work for the Concrete Centre. I spend quite a lot of my time giving guidance about how to specify sustainable concrete. So I'm going to spend a few minutes now just running through some of the issues to think about when you're specifying concrete, but also designing it. Most of that is going to be about reducing providing sort of low carbon concrete. So by that I mean low embodied carbon. There are many different aspects to think about sustainability. Biodiversity, low waste, resource efficiency, and all of them are going to vary according to the type of building that you've got or what your client requirements are. I think carbon probably has risen to the fore as one of the key aspects to think about. It certainly forms, in terms of operational CO2, forms the backbone of BREEAM and Code for Sustainable Homes, and of course the other government initiatives for zero carbon homes and zero carbon buildings. They're all about operational CO2, so that's the carbon resulting from the energy use of a building. Embodied CO2 and operational CO2 need to be looked at together to form the whole life analysis of a building. At the moment, operational CO2 is still by far the largest aspect. It's the carbon resulting from the energy use of a building is the largest slice of the pie. And concrete is very useful in reducing that. There's a lot in terms of producing energy efficient design strategies. Thermal mass, for example, the concrete is very high in thermal mass, and it's a pretty well established means of reducing the heating and cooling load of a building through the use of concrete and nighttime purging as well. There's lots of very good examples out there, particularly important if you can optimise passive solar design. Good housing examples such as Bedstead and various other ones dealing with that. It's an established means of reducing energy use within a building. Of course, thermal performance is also important, so we've got plenty of guidance from the Concrete Centre about how to use thermal mass, but also how to improve the thermal performance of a building and the building envelope, so by air tightness, good U values, reducing cold bridging, things like that. So it's an important aspect of it. So think about whole life performance when you're designing. And generally there are studies out there, Arup did one a few years ago looking at some housing, which proved that concrete will give you a lower whole life carbon footprint if you're considering the whole life performance, so looking at embodied CO2 and operational CO2. But as we are tackling through legislation, operational CO2, embodied CO2 is becoming increasingly a larger slice of the pie. It's becoming more important. So we do need to think about it. And so that's what I'm going to focus on specifically in this presentation, about how to think about that when you're specifying concrete. Now, there are many different types of concrete, and each of those have very different corresponding embodied factors as well. So the sustainability credentials of your concrete is very much going to depend on where you're getting it from, but also what type of concrete it is. Blockwork, hybrid, precast, coloured, sprayed, all those different things can be very different. If you're buying a product, actually a lot of the information will be provided to you by the manufacturers. There are lots of A and A+ rated products out there, and they've got very high recycled content. All this information will be increasingly being able to be made available to you as well. If you're specifying concrete from scratch, it's important you need to understand what the concrete is made out of and how you actually specify all of the constituent parts. We've got a very good document about that, which is what I'm mainly going to be basing the rest of this talk on, which is called Specifying Sustainable Concrete. And you can download that from our website, the Concrete Centre website. Now, concrete as by volume, I'm showing a slide now that shows broadly by volume the average mix is included within concrete. So about 10%-ish of cement. That's going to depend a little bit on the mix that you've got. Some water in there, some air. But by far the highest ingredient, or the largest ingredient, is aggregate. So that's fine aggregate, sands, coarse aggregate, which are called gravels. Of course, a lot of concrete also has reinforcement in it, steel reinforcement. It might have some pigments. And possibly some additives as well. Understanding sustainability credentials of all of those different aspects is important to understanding what your final concrete is going to be made out of. There's a useful table within the document that I referred to, which gives a breakdown of all of the different embodied CO2 figures for the different aspects of concrete. And what you can see there is the Portland cement, so that's pure cement if you like, is by far the highest aspect there, 930 kilograms per tonne. Actually, that figure is a little bit out of date. These are 2007 figures. And I'll explain later, the industry have been doing a lot to reduce the embodied CO2 of concrete. So it's lower than that now. But what you can see there is that there are other aspects, there's what they call cementitious constitutes or cementitious additions. GGBS, which is ground granulated blast furnace slag, has just 52 kilograms per tonne. Fly ash, just 4. So one of the key aspects to specifying low carbon concrete is to use cementitious blends, so mixing the Portland cement with some of these other elements, which actually are byproducts of other industries. You note there as well, aggregates 4 is very low in embodied CO2, and reinforcement 427. As I said, the industry have been doing a lot to reduce the embodied CO2 of cement, and in fact it's reduced by, I think, over 55% since 1990. The way they've been doing that is to use alternative fuels. That's a big key part of it, so using waste to burn to make the cement. So that's good news. But as designers, we can actually improve the embodied CO2 of our concrete even further by specifying particular types of blends, which is what I referred to. So ground granulated blast furnace slag is a byproduct of the steel iron industry. It's very low in embodied CO2, as I showed before. And in fact, if you use a blend, say 50% mix, by replacing 50% of your ordinary cement with GGBS, you'd be reducing your embodied CO2 of the concrete by over 40%, just by that simple move. So that's a certainly useful thing to think about. Also, there are other benefits. It actually makes the concrete inherently pale and creamy, so you get a much lighter concrete. So if that's used on the inside of a building, where you would be putting your concrete to improve the thermal mass, you can also improve the light reflectancy of the internal space as well, which is a useful thing to think about. It's part of your overall design. The other very commonly used cementitious additional part of the cement blend is fly ash, and that's a byproduct of the coal-fired power stations. Again, low embodied CO2. A great example of this is the Angel building, used a 34% mix, and that's a great building to go and have a look at for visual concrete too. So a key consideration when you are thinking about specifying concrete is to consider using cementitious blends. The only thing you need to be aware of is that for cement blends that have a very high proportion of these cementitious additions like GGBS or fly ash, it might affect the striking time. That's only going to come into play at percentages over about 40%, but that does depend on whether it's in the summer or the winter, but perhaps also on the profile of the concrete itself. So as a general rule, 40% is the thought. So that's cement. It's one of the key aspects to think about. Now aggregates, as we said, is by far the largest proportion of the components of concrete. It's inherently low in carbon, and actually in the UK we're blessed with having potentially thousands of years of supply. It's very plentiful, naturally occurring, and it's local, which is an important sustainability credential. Through the BREEAM and various other considerations, recyclability and using recycled content has come to the fore. And it's one of the questions that we get asked quite a lot is how much recycled content can we use in concrete, and where do we get hold of it? Now, the difficulty is that actually we're already really good at using recycled concrete and recycled aggregate within the UK, 3 times better than the rest of Europe. It's very hard to get hold of it. Concrete is 100% recyclable, but it tends to get used in hardcore or various other different uses, very usefully around the building. Often gets demolished and then put in the landscaping, for example. Now, this isn't necessarily a bad thing in terms of sustainability, in that actually because virgin aggregates or local aggregates are so low in embodied CO2, they're very likely to have a lower carbon footprint than if you were using the recycled aggregates. So unless you can source your unless you can find a good, a steady source of recycled aggregate that's very close to your site, so within 15 kilometres, then actually a local source of virgin aggregate is going to give you a building or concrete that's lower in carbon footprint. There is an alternative. There's also secondary aggregates. There is a very good supply of these down in Cornwall as a byproduct of the kaolin industry, called granite sands or granite aggregates. But again, one just needs to consider how you're going to get that to your site in a low carbon way in terms of transport costs. Concrete is a local material. We are self-sufficient in the UK for all the raw materials for concrete. We don't need to import anything to make concrete. I think white cement is the only thing that we actually do import, and that's not typically used for in-situ concrete. Also tied in with that, of course, then is responsible sourcing. And I would say this is something that specifiers should think about when they're specifying concrete, is to state that your concrete is responsibly sourced. 92% of all concrete in the UK is responsibly sourced at the highest standard, which is BES 6001. And that is the BRE accreditation system that includes not just traceability of materials, where it's coming from, but also a stewardship right the way through the whole process, and includes ethical as well as responsible sourcing. I would also specify for reinforcement responsible sourcing through the CARES or eco-reinforcement system. Reinforcement is an important part of concrete specification. About 50% of all concrete is reinforced. And but practically all of that steel is recycled, and it's produced using a low energy electrical arc furnace process. So that's the important part of that specification. Admixtures, I'm not going to say too much about that. Admixtures and water, they are an important part of it. Admixtures are typically so low in their the amount that they're included into the concrete that they don't need to be added into the embodied CO2, but they can have a really major impact. They can improve the strength, which means in terms you could potentially reduce the amount of cement that you need for a mix, for example. A very common one, superplasticizer, is very useful at reducing the amount of water. And focus on water is going to become increasingly important in the considerations of sustainability, and they already are. In the concrete industry are doing a lot to look at that as part of their new focus of their strategy. The reason why I'm able to put all these facts and figures in front of you is because the industry have been very good at measuring and reporting sustainability data. The 5th annual sustainability performance report has been published, and this is all part of their industry sustainability construction strategy. Last year they set new strategies and new commitments for their industry for meeting a 2020 target, and within that there's been some commitments to providing life cycle analysis information, low carbon freight initiative, and also looking at water strategy development. So fantastic things that the industry have been doing in terms of sustainability. One of those figures that came out of that actually was this amazing figure about waste. Concrete is a low waste construction solution. The industry in 2011 used 63 times more waste than it actually produced, which is an extraordinary figure. Very little goes into landfill. It's 100% recyclable. And in fact, that's one of the things for designers to think about when they are considering sustainable construction, is then also designing solutions that are going to be low waste solutions. Concrete is very easy to recycle on site, and it's a very useful product, as I said, for used on site. RAP produced some good guidance. We've worked with RAP to provide some low waste construction solutions. And this is leading on to the next aspect of thinking about how you design with concrete sustainably, and that is what framing systems do you use? What type of concrete do you use within your design? What is the most sustainable one to use? Arup did a study in The Structural Engineer. There's a very good article there. And comparing different structures. So they looked at one design for a commercial property, a hospital, and one for a school, and then and managed to do something that we'd never get a chance to do when we are actually in practice, and that's to model each of those using 8 different structural frame solutions, combination of short span, long span, concrete, and steel, in order to be able to establish, well, what is the difference in embodied CO2 between those different frames. And what they came out with was that they're broadly all the same, which is quite interesting. I mean, that is a very headline result for that summary, but long span generally came out as being consistently slightly higher, irrespective of what material it was made out of. But also what the results that came out of that was that for concrete, any of the concrete frame solutions, is the designer has a greater potential to reduce the embodied CO2 through their design, which is significant in that if you take on board some of the things I've already talked about in terms of using cementitious blends and type of aggregates that you use, and that you can have a significant impact on your frame design, reducing it in terms of embodied CO2. And of course, don't forget, this is just about the frame. This isn't then the impact of the frame can have on the design. So the fact that you've got concrete exposed slabs, say, means that you can also then reduce the embodied CO2, so further savings. So you can't just think about these things in isolation. As with all elements of design, you've got to think about it holistically. And that's where also thinking about the type of framing solution that you use, what are the other impacts that would have in terms of the energy use of a building, say, or the embodied CO2. So take, for example, void formers. That's a way of being able to make the structure lighter, so you're reducing the amount of foundations that are needed, but still get all the benefits of the concrete within the frame. Post-tension slabs is another one to think about. In fact, these really come into their own in very tall structures, so anything over 10 stories, because the floor plate is so much shallower, you can actually gain an additional story, or rather you could lose an additional story, still provide the same amount of accommodation for your client, but save all that embodied CO2 of the associated cladding and other services associated with that design. In fact, normally what happens is you end up putting an extra story in. But that's useful. That's good resource and land efficiency as well. Post-tension slabs are flat slabs, so they provide flat soffits. And again, that's another way of thinking about it. Flat slabs are part of, as well as being a very efficient way of designing building, by avoiding the need for ring beams, for example. Your glazing can go up to the ceiling height, which means you're able to get more light into the space, which reduces the amount of artificial lighting you might need in the design. Avoiding downstem beams means that services are able to go in more efficiently, apart from the actual installation being faster. But if a pipe if an extract vent doesn't have any bends in it, it's going to run more efficiently. So again, that's an improvement on operational CO2 and more efficient running of a building. So it's not always understood that structural designs are going to have an impact on the energy use of a building. It's not always put together as a thought process when you're designing, but increasingly those are the sorts of things we all need to be thinking about as designers. Of course, the other aspect of concrete, thinking about the whole process holistically, is that it's incredibly material efficient. So if you take a concrete wall, that is providing you with your structure, and it's a durable, low maintenance solution, but also it's probably going to exceed those minimum standards that you need for fire separation, for acoustic separation, as well as providing you with some thermal mass benefits. And of course then, if that's exposed, you've saved on all the embodied CO2 that's associated with the additional finishes of installing it or maintaining it over the life of the building. Some of the carpets, for example, are relatively high in embodied CO2 and have a design life of 7 years, I guess. So exposed polished concrete floors have a real impact in that regard. So another point to consider when you're designing any buildings, I think this is something that's quite close to my heart, is sustainability is about optimising resources. You need to use resources to build anything. So making the best of it has got to be a key sustainability strategy. And the thing about concrete is it lasts for a very long time. So we're already beginning to see a lot of this now with buildings with the retrofit work that's going on. Is to use structures and reuse them, breathe new life into them. Those buildings, if you're lengthening the life of a building, then what are you doing actually to the effective embodied CO2 of that structure if that building is then lasting for another 50, 60, 100 years? So a lot of existing structures are being reused in that way. But actually, shouldn't that be the way that we're designing in the first place? I certainly believe so. And that's designing for a long life. Clearly is an important factor and something to consider. That structural frame that could have its cladding removed and reclad using something that's more efficient or just different or appropriate to the new building use is in there. Consideration of the structural frame, its adaptability, future layouts. That robust structure has a capability of lasting for very much longer than its initial design life. Obviously, tall floor-to-ceiling heights are important as well, particularly if you're going to be naturally ventilated, but also to allow future adaptability for other building types. So that principle of long life equals low carbon is something I really believe in, and I think is certainly something to be considered, particularly for the use of concrete, because it can last a very long time. And I just put in as my last slide, of course, a very ancient old concrete building, And a reminder, it's been around for a long time. That's be interesting to see if anybody's ever worked out what the carbon footprint is of that. But of course, that is sustainability in its true sense. It's been around for a long time. And in fact, of course, the Romans used ash in their mix, which is something I've already talked about. So hopefully that was of use to give you some ideas about the sorts of things to be thinking about as you're designing through the design. And it's just a reminder that sustainability is not a single issue. It's quite complicated. And I think the decisions that you make are going to be dictated by lots of different aspects. But obviously carbon being an important part of that as well. Okay, thank you.